Hello, everyone. I like the room full of people. I'm going to get started. And my name is Satoru Isaka, and I'm going to be talking about taxonomy. So why taxonomy of robots? Why should you be interested in this? That's because we have full of machines in our ecosystem. And in fact, there are so many machines in our world that the time has come to name them, identify them, classify them, so that we can deal with them. Now, for biological systems, biologists do care about the systematics, the taxonomy, just like the Linnean system that we have. So we can identify plants and animals. So when we see them, we know what they are, we know how they are related, and we can study them. When it comes to robots, it is surprising to know that there is no classification system for robots. Now, it is true that there is a set of classification mechanisms set by standards organizations like ISO and IEEE. But it's all fragmented because of the difficulty of defining what a robot is. Because a robot is a polysemous, meaning that it has a lot of multiple meanings depending on the context. So without the context, it is very difficult to point out what exactly a robot is. Let me explain a little bit more. The dictionary definition of robot is already pointing out it's a polysemous. It could be a machine, or it could be people, or it could be device. And for the community of systems man and cybernetics, obviously, the systems that perform tasks autonomously or automatically is what we mean. So that is the context. But to go into deeper level, standards organizations have different ideas of what a robot is. Now, I'm not going to read all these things, but the point is, robot is very difficult to define, scientifically speaking. So the question is, can we build a universal taxonomy of robots? So that's my interest. And I say, yes, yes, we can. And here's how. We need to consider three things. First, we need to broaden the concept of robots beyond what a robot is to the level of autonomous systems. Because robot is so difficult to define, depending on the context, we can't just build a taxonomy specifically for robots. We need to define taxonomy for autonomous systems, which is a broader class of machines or systems. Second, we need to set the right perspectives to build a taxonomy. You can't just pick and choose particular perspective for convenience. We have to have a more global, general, universal perspectives that can comprehensively define what an autonomous system is. And for that, I proposed three biologically grounded perspectives. One, anthropogenic perspective. Two, ecological perspective. And the third, phylogenetic perspective. And number three, we'll build taxonomy from these perspectives and then combine them in a faceted structure so that it can function as a classification system. So here is the result. This graph, or this diagram, shows the taxonomy of robots and autonomous systems. Now, this is a small diagram, so let me dive into a little deeper into some of the highlights, some of the features of this taxonomic system. What I did was to identify 6 fundamental dimensions of autonomous systems. These dimensions are derived from 3 perspectives, as I mentioned earlier. The anthropogenic perspective provides us the dimension of autonomy, communication, and domain. The phylogenetic perspective provides us the two-dimension, body and function, and the last, environment, is the ecological. So let me start with the easy one. In the dimension of environment, we can build a taxonomy that identifies what type of environment does a robot or autonomous system behaves. So space, atmosphere, outdoor, indoor, underwater, underground, and of course, there's a virtual software environment. So not only I'm talking about the physical robots, I'm talking about software systems as well, because they are, in a global sense, autonomous systems. For body, I take a very high-level view of what an autonomous system can be in terms of the barrier between internal and external systems, internal environment. So I'm looking at a hard shell, like a typical industrial robots, or the soft shell, which we are looking at into soft robots and flexible robots, and organic and nano as well. Today's keynote speech had this organoids. That type of system belongs to that organic level. And none, meaning it's a software. There is no physical boundary between environment, external, internal environment. And for functions, I'm looking at mobility and manipulators. And then again, it applies to software as well. Now the software can be mobile, meaning like a malware, the virus. They are mobile software. There are static software as well, so they can be classified in that sense. For domain, I borrow classification or taxonomy from the ISO standards. They are industrial robots, industrial machines, service machines, medical machines, and so on. For communication, again, I'm taking a really high-level taxonomy by looking at what type of interface does the system have in terms of a human interaction or intervention. Does it have a direct interface, like buttons and screens and touch buttons? Or does it have a remote control feature that is an indirect interface? Or sometimes there is no interface. In this case, these are embedded systems. And lastly, the autonomy. Now, this is the main line of research of mine, and this is outside the scope of this presentation, but I will show you the reference to describe the details of this. This is actually quite a big subject to talk about. But for this conversation, I will just highlight there are 4 levels of autonomy: non-autonomous, intermittent autonomous, eventually autonomous, and fully autonomous. In my paper and the different papers, I clearly define what these mean and why they can be useful. Just for the clarification, most machines today that we deal with, including autonomous vehicles, they all belong to intermittent vehicles, intermittent autonomous system. Currently, there is no fully autonomous systems exist except the biological system that we humans did not create. So just to kind of give you an idea of what this classification and identification system can do for us, I'll give you an example. So let's talk about a vacuum cleaner, the household vacuum cleaner that's shown in the slide, thing that every day that we use. I present to you an identification code depending on the taxonomy on each of the 6 dimensions. So based on that system, that particular vacuum cleaner has an identification code of AN, BH, CD, DS, LI, FNM. And of course, they don't mean anything by itself. The first AN represents the type of autonomy. The BH represents the type of hard shell body or type of body that it has. The CD represents the type of communication. DS represents the type of domain. ELI represents type of environment. And FNM represents the type of function this system has. Now, what about the mobile vacuum cleaners, which is slightly different, in our opinion, of the handheld vacuum cleaner? In this case, the code becomes this. Now, it's hard to see what that means, so I'll give you a comparison. The handheld vacuum cleaner and the mobile vacuum cleaners are different in 3 dimensions: autonomy, communication, and function. By having the type of coding systems that I'm presenting to you, it will show the difference between the type of autonomous functions, autonomous systems they are. I'll give you another example. I'll give you this code. And this code is may not mean much, but it says a lot. It is non-autonomous. It has a hard body. It's got a direct interface. It's got a transportation domain. It's used outdoor, and it's a mobile system, but it doesn't have a manipulator attached to it. So this code itself is showing a lot about a particular autonomous system. And perhaps a regular automobile belongs to this type of code. So what if I change the code a little bit on 2 dimensions, change that to intermittent autonomous, and change that to indirect autonomous? What would happen? The car becomes a robotaxi. That is the autonomous vehicle that can intermittently autonomously behave, and it is remotely accessible because there is no direct control by the driver. I'm speaking of a Waymo, Google's Waymo robotaxi. So what I have shown today is that I have proposed a taxonomic classification identification system for the robots and autonomous systems for the purpose of public safety, meaning that we as a manufacturer, designer, or researcher of systems, autonomous systems and robots, we are responsible for communicating properly what functions, what risks, what uses does the system we're building offer to the end users, and also for the purpose of effective R&D design of the future. At the end, I'm going to show you a little fun entertainment QR code for you. I created a Notebook LM's podcast feature and talk about my paper. So if you QR code this, it will go to a podcast, 9 minutes podcast to talk about this AI conversation about this particular paper that I wrote. And the 2 other references that I'm shown on the figure slide is about the autonomy that I did not have a chance to explain to you today. Okay, that's it. Thank you.